So here's our next problem. So what I have here, uh, so this would be a base, and here's like a floor around here. And coming out of the floor is a little rod, massless rod, so we're going to ignore it. But connected to that is this cross rod right here. Okay? And so it's 4 feet long. And what's happening is we have this like bowling ball. And it's going to come in, and it's rolling, 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 and it's going to, right at the end of the rod, it's going to impact it. And this rod here, the connection down to the ground, is that it can twist, so it can freely rotate. This piece can rotate around and around and around. All right. So this ball, which has a half-foot radius, is going along at 6 feet per second coming in for this end. All right. So since it's going to hit here, so the radius, naturally, that this piece supporting this rod, half a foot. So they're going to impact right in the end. And you'll notice we have the coordinate system set up along the rod. So here's the x-axis going this way. Perpendicular to that, perpendicular to the rod is the y-axis, and the z goes off like so. Okay, so what are we told? The ball weighs 3 pounds, again 6 feet per second. It's going to strike a smooth rod, so there's no friction that's going to be affecting this impact. And the bar is at rest. Okay, determine the omega of the bar about the z-axis, because it's going to twist like so, where coefficient of restitution is 0.8. All right? So here's the thing that confuses people. So we got G. G is translating, and G is rotating. Okay? Picture as it's just rolling in. Well, this is rolling. What is the axis this thing is rolling in? It's rolling in the x-axis. It's not coming in with the spin this way. Okay, it's not like a gyro ball. So we're going to be looking at what this bar does. So we're having rotation in the z. So when we go to do angular momentum, we got to understand you just don't pile all the rotation together. You only look in given axes. So we're only going to be concerned with how this twists in the z. This thing has absolutely nothing going on in the z. The ball is not jumping or falling, so we don't have any of the translation in the z. And we don't have any rotation in the z. Only the bar does. So that's really important. So this is a problem that will confuse people. But when you go to look at the angular momentum in this problem, because basically this thing is going to be translating into this bar. So far as it knows, it's just a block sliding along. The fact it's rotating, rolling to get there, bar doesn't know that. All right. This bar, when it gets hit, is going to rotate in the z. So we need to look at everything and how it rotates in the z. Well, there's nothing but the bar. All right. So omega of the ball, since it's going at 12 feet per second, given r, well, 6 divided by 0.5 would be omega, so that gives us 12 radians per second, but along the x. Okay? And actually it'd be in the negative x, because picture is it's going like this, so it's rolling this way. Use your right hand, roll with it. We're pointing in the negative x direction. All right. So I should put a minus sign in here. All right. So omega z in the z-axis for the ball, 0. Therefore, the angular momentum when we go to look at this ball, 0. All right. So we have an impact that's going to be taking place. Let me move this up, get a little more space to work with here. So angular momentum will be conserved. The forces between the ball and the rod here are internal, so they do nothing, and so there is no external no external forces causing a moment about the z, or anything that if we were to integrate it, because the integral of the moments with time, the impact will be virtually instantaneous, so the integral is 0, so we conserve momentum. Okay. So we have this bar. We are going to be looking at relative to the center of the bar where the rotation happens. So mass moment of inertia about the center is 1/12 ml squared. We have that there. So there's that all computed for us. And so now we can go and use our equation for angular momentum. So initially, before the impact, bar, no angular velocity, so we get a 0. So then we would do r cross v. Okay, so picture here's r going from here to there, and so we'd take our right hand. This is kind of hard to show. So our right hand would go out this way, and then we'd roll it in the direction of the velocity. Bottom line, we're going to get a negative z. And that's what we have here. So we have r is 2, mass 3/32.2, velocity 6. Vector-wise, turns out to be negative. After impact, the bar will have some omega, so we call, here's I, omega. And again, RMV, where now the V ball is unknown. We're going to figure that out. All right. Now we'll note that this angular velocity, because we're going to be doing an impact problem, so the impact, when we use the coefficient of restitution, is all in terms of velocities. So this is inconvenient. We'd like to get this in terms of a velocity, and so I note here that the omega here, we can express that as, this is a point B in the text where I took this. I'll leave that. Here's point B. So if we have the velocity of B here, divide by 2, we would have omega. All right. So that sets up us taking a look at the coefficient of restitution. All right, so I took this, simplified it down to that. Coefficient of restitution, 0.8 is the coefficient of restitution. So that would be velocity on the bar of point B. That's up. Oops. That'll be right there. Minus the velocity of the ball after impact, divided by the velocity of the ball before impact minus the velocity of the bar before, which is 0. So this gives us two equations, two unknowns, and there was the result at the bottom. Just a little bit of algebra. That's all for here. I'll have other problems coming up right behind this.